So friends, now after understanding the ideal gas behavior of various gases, now we are coming to a point where we can say that even if these gases are showing some of the properties, these properties cannot be applied for the gases which exist in a nature, like gases like hydrogen, carbon dioxide, nitrogen, oxygen, acetylene, ethane, methane and so on. So these gases which are not showing properties or which are not behaving like ideal gases are called as real gases. So for a wide range of temperature and pressure, these gases are not obeying Boyle's law, Charles' law, Fischer temperature law, Graham's law of diffusion, even the kinetic theory of gases. Now what is the reason behind it? There are certain assumptions which were made by Maxwell, Boltzmann and various other scientists are not validated by using the real gases, and that is the problem where the real gases are not showing the properties of ideal gases. The first satisfactory explanation was given by van der Waals, and for that purpose he has pointed out some of the properties or some of the assumptions which were made in a kinetic theory of gases, they were wrong. And what are those assumptions that we are going to discuss now? Before we proceed for that, let us consider our equation PV is equal to nRT. So that is our ideal gas equation. So now we are going to use the ideal gas equation. The equation is PV is equal to nRT. Now we are going to consider one ratio, PV by nRT is equal to Z. So for 1 mole of a gas, this becomes PV by RT is equal to Z. Z is called as compressibility factor. As we know that gases can be compressed because the molecules are far away from each other, and therefore after applying pressure or by decreasing temperature, the gas molecules come close to each other and therefore volume can be decreased. So let us consider PV is equal to nRT, that is so it becomes 1 mole of a gas. So I consider this volume as molar volume Vm. Now this is for ideal gas. So in an ideal gas we know that Z is equal to 1. Okay. Now for real gas I can say that PVm, so I will put it as a V dash m divided by RT is equal to Z. This is for real gas. So if we take the ratio, okay, now for ideal gas Z is equal to 1. For ideal gas Z is equal to 1. So we can write here as Z, we will take a ratio now, Z upon 1 is equal to, what can we write? P Vm dash upon RT divided by P Vm divided by RT. So Z is equal to what? Z is equal to V dash upon Vm. But Vm is equal to, so Z is equal to V dash for n moles of a gas, for n moles of a gas Z is equal to V dash m upon, so I will put here. So what can I say that Vm is equal to nRT upon P. Now this is a very important relation. Further I can write this as Z is equal to V dash P upon nRT. This is a very important relation. From this we can get the idea, after applying pressure and temperature, which gas is compressible or which gas is more compressible or which gas is less compressible. Okay. Now by considering this, we can plot a graph, and those graphs consist of if relation or variation of Z with pressure. Okay. So let us consider one graph where we are plotting Z versus P, and this is for various gases. So for ideal gases we know that the value of Z is equal to 1. Now what are those gases? So if we plot a graph Z versus P, for hydrogen I will be getting this graph, for helium I will be getting this graph, for N2 we will be getting this graph, for CO2 we will be getting this graph, for CH4 we will be getting this graph, and so on. So if you observe carefully, none of the gas is actually showing ideal gas behavior, and basically all these gases at high pressure are largely deviating from the ideal behavior. Okay. So this is one concept. Now why this is happening? This is because in a kinetic theory of gases, we consider that there are no interacting forces between the molecules. There are no interacting forces between the molecules. So here the molar mass is more. So here we have to consider the forces of attraction, and that forces of attraction makes these gases real, and rather these gases are not showing a linear relationship where Z is equal to 1. They are largely deviating. Okay. Now if we plot another graph, let us consider a graph which is plotted same Z versus P, and we know that Z is equal to 1 for ideal gases. Now this graph is plotted for nitrogen gas at different temperature. Okay. So let us consider we have, this is T1, this graph is for T1, this is T2, this is T3, and this is T4, where T4 is greater than T3 is greater than T2 is greater than T1. So what does it suggest now? It suggests that as the temperature increases, gas is closing near to the ideal behavior. Similarly here also if you observe at low pressure, especially for hydrogen and helium, you can observe at low pressure the gas is tending towards ideal behavior. Now why this is happening? Same concept. As you increase temperature, what will happen? The intermolecular distance between the molecule goes on increasing. So as the molecules are away from each other, the interacting forces decreases, and we know that if there are no interacting forces, the gas become ideal. Therefore, one conclusion we can make from these two graphs. What is that? Gases real gases, obviously we are talking about now real gases become ideal at low pressure and high temperature. Low pressure and high temperature. That means this equation for ideal gases is not valid for real gases. Now, there will be correction in pressure as well as in volume, and that correction is actually given by van der Waal. Okay. So, here from this concept there may be some questions, and those questions are actually which of the following gas is more compressible, which of the following gas is less compressible. Such kind of a questions will be there. Under certain pressure and temperature, let us consider this relation. Now, we know that Z is equal to V dash. So, when I am saying Z is less than 1, means it is more compressible. So, we need to understand this part. Significance of value of Z. So, as we know that when Z is equal to 1, it is ideal gas, right? When Z is greater than 1, okay, just see here, Z is greater than 1. So, what will happen? V dash P is also large. So, we can say that gas is less compressible. Okay. Similarly, when Z is less than 1, which means gas is more compressible. Now, if you observe carefully this graph, you can easily identify this. You know, hydrogen and helium, Z is greater than 1 for those gases. They are very small molecules, and because of that the interacting forces between them is very less, and therefore they are less compressible. Z is greater than 1. CO2, CH4, NH3 high molecular mass, so they can easily come close and get condensed, get compressed. So, if you observe over here at moderate up to moderate pressure, Z is less than 1, so gas is more compressible. Okay. Now, what is the pressure correction and what will be the volume correction, that we have to discuss, and what are the assumptions for those corrections, that also we have to consider, and on that basis we will be getting new equation for real gases, and which was accepted all over the universe. So, that we are going to discuss in the next session. Thank you.